Hello everyone and welcome to this session on deep network architectures. Today we are moving beyond standard feed-forward networks to explore specialized deep architectures. We will cover recurrent neural networks, recursive neural networks, restricted Boltzmann machines, deep belief networks, and close out with a practical case study on dialogue generation using LSTMs. Let us jump right in. Here is our agenda for today. First, we will look at the foundation of deep network architectures and why depth matters. Second, we will examine recurrent neural networks and how they model sequences over time. Third, we will transition to recursive neural networks for handling tree structured data. Fourth, we will cover restricted Boltzmann machines and deep belief networks as generative energy based building blocks. Finally, we will tie everything together with a case study on LSTM based sequence to sequence dialogue generation. To start with our foundations, deep learning works by stacking multiple layers of representations, building up simple features into complex abstractions. Crucially, different data structures demand different architectural designs. For sequential data like text, speech, or time series, we use RNN and LSTM to carry memory forward step by step. For a structured or a tree-like data, such as sparse trees, we use recursive networks to compose representations along hierarchies. And for unlabeled data, RBMs and DBNs allow us to learn probability distributions layer by layer. Let us focus on recurrent neural networks. Unlike feed-forward networks, and RNN processes sequential input one element at a time, feeding its hidden state back in as input for the next time step. This gives the network a form of memory. Key traits of RNNs include weight sharing across every time step, output at any given point depends on all prior inputs, training via back propagation through time. However, standard RNN struggle with long range dependencies due to the vanishing gradient problem. So, how do we address that limitation? The problem is plain RNN repeatedly multiply gradients across steps, causing them to shrink toward zero or explode, effectively forgetting early context. The fix is modern architectures like LSTM and GRUs introduce gating mechanism, input, forget, and output gates that explicitly regulate what information to keep, discard, or expose. The payoff is gated networks can retain context across hundreds of steps, making them incredibly practical for language processing and dialogue modeling. Now, let us look at recursive neural networks, not to be confused with recurrent ones. Instead of unrolling linearly over time, a recursive network applies the exact same weight matrix recursively over a tree structure, such as a sentence parse tree. It merges child representations into a parent representation at every node. This makes it ideal for hierarchical data, capturing compositional semantics or how individual word meanings combine into overall parse meanings. The only requirement is having a known or predicted tree structure to guide the computation. To clearly summarize the difference between recurrent and recursive networks, the structure is RNN process linear sequence chains, whereas recursive networks operate on hierarchical tree graphs. In typical use, RNN excel at a time series and text streams. Recursive networks target parse trees and nested scenes. In case of weight sharing, shared across time steps for RNN versus across tree nodes for recursive networks. In depth and order, RNN depth equals sequence length in a fixed left to right order, while recursive depth equals tree height based on explicit tree structures. Shifting gears to energy-based models, let us talk about the restricted Boltzmann machine, that is RBM. An RBM is an undirected two-layer generative model consisting of a visible layer and a hidden layer. It is restricted because there are no connections between units within the same layer, only between visible and hidden units. It learns a probability distribution over the input data by minimizing an energy function using an algorithm called contrastive divergence. RBMs are historically significant for pre-training, dimensionality reduction, and collaborative filtering. When we stack multiple RBMs together, we form a deep belief network, that is DBN. DBN are trained using greedy layer wise. Pre-training, each layer's hidden output becomes the visible input for the next layer, constructing a deep feature hierarchy from raw inputs up to abstract representations. Why stack them? It provides an excellent weight initialization before supervised fine-tuning and allows the model to learn feature detectors without labeled data. DBNs served as a crucial foundation for early, deep unsupervised learning. Let us bring these concepts together with a practical case study, that is dialogue generation using LSTM. Here, the goal is, given a conversational history, generate a fluent context-aware reply. Then, why LSTM? Since conversations are sequential, LSTM gating preserves a relevant context from earlier turns while filtering out irrelevant noise. Here, the framework is modeled as a sequence-to-sequence architecture. An encoder LSTM processes the input utterance and a decoder LSTM generates the response. The training data is large corpora of paired dialogue such as chat logs or subtitles. Then the next case study here is how the encoder-decoder pipeline functions in detail. Tokenization, the user's input is split into words or subwords and mapped to dense embedding. Encoder LSTM reads the sequence and compresses it into a fixed length context vector. Decoder LSTM reads reads the sequence and compresses it into fixed length context vector. Then the decoder LSTM uses that context vector alongside previous tokens to generate the reply token by token. Next, the sampling or ranking techniques like beam search select the final output from candidate token. This context vector handoff remains a core principle behind modern conversational AI systems. Evaluating the approach gives us useful insights. The strength are, it captures short to medium range context, produces fluent responses, and is fully trainable end to end. The limitations are, baselines can default to safe, generic replies like I don't know, struggle with long history, and lack external knowledge memory. While modern systems often swap or augment LSTM with attention mechanism and transformers, this encoder decoder foundation established the framework we still use today. To wrap up our session today, here all the key takeaways are: RNN and LSTM handle sequential data with memory over time. Recursive neural network capture compositional hierarchy along tree structures. The RBM serves as a two-layer energy-based generative building blocks, and DBN stack RBMs to learn unsupervised feature hierarchies layer by layer. And dialogue sequence to sequence models leverage encoder decoder LSTMs to turn conversational history into natural responses. That's all about today's presentation. Thank you.